Welcome everybody to Calculus 3. I'm your instructor, Matthew Burkemper. You can just call me Mr. Burkemper if you prefer, or you can even just call me Matthew. I'm not going to be too concerned with that. But I want to start off with emphasizing some of the main points that I mentioned in the announcement email that should have gone out to everybody. First, on the subject of our lecture videos. So this is going to be our format. Oops. This is going to be our format for the semester. You might, as you kind of saw there, I'll probably make a few mistakes in all this. I'm not a professional video maker, but I'll do my best to provide you with the content that you need for the semester. I will be providing links to each of these videos on Blackboard. And they will be links to the YouTube channel that I have set up for lecture videos. You can subscribe to that channel if you prefer, but on Blackboard I will also have PDF copies of this work that I'm generating right here, all the documents, all the actual mathematics that I work out for you. Those will be in a PDF format on Blackboard. So it's probably preferable if you go to Blackboard to get to the videos. The links to those PDFs will be literally underneath the videos, the links to the videos on Blackboard. It's important for you to keep up with the videos, mostly following the schedule that is in the syllabus. There's a syllabus that has all the lecture, all the weeks that you should be paying attention to these videos. So this particular week we have the chapter 12 review, which will cover section 12.1 to 12.4. The main reason that we're going to be covering all those four sections is because those are, which is I'll state, those are also included in Calculus 2. I'll talk about that when we actually get to the content after this introduction. But it's up to you. You are the one that has to keep yourself on schedule to actually pay attention to these videos, watch these videos those weeks, and then do the homework that will be based off of the videos that are posted for that week. Which, that's the second thing, online homework. So you probably have seen this before if you took Calculus 2, which does state, but our book comes with WebAssign. It's an online homework system. You'll need to make an account on the WebAssign website, and I like to go ahead and use the link that I'm putting here. If you go ahead and use that address, it'll take you to it. I mean, it'll actually redirect you, I believe, but the point is that it'll take you where you need to go. You'll need you'll need an access code that will usually comes with the book, or if you haven't purchased the book, you can just actually purchase the access code itself directly from WebAssign. And there will be an ebook in the system. If you just want to use the ebook, you can save yourself some money and just get the access code. I actually think that's a good idea because these books tend to be a little bit more expensive than I think they ought to be. So if you do want a hard copy, it's your money. You can get one, but if your money isn't concerned, just go ahead and get the access code. You do need that access code though. The homework is important, and you can only get to that if you have that access code. Along with the access code, you also need our class key. This will tell WebAssign which class you actually are in. That will start with Wichita, and then it'll be sorry, I don't know how I got those backwards. 6835 and then 8626. This is in the syllabus too, but that's the key that you need. My plan, like I said a little bit earlier, is to have weekly assignments that will be based off the sections that I tell you to watch the videos for, and I believe I will have all the assignments due the following Wednesday. So the first homework is not up yet. I will get that up relatively soon, but technically it'll be due on, sorry, it'll be posted as if it is assigned this coming Friday, and then it'll be due the following Wednesday. So it's not a big rush right at the moment. But I do want you to go ahead and get signed up as soon as possible. I'll be keeping track of whether people are signed up or not, and I want to see everybody on there. Next is exams. There's going to be 3 exams. One of them is the final. They're going to be the only part that is in person. I will need you to actually come to our South Campus class, our South Campus location, and take those in person with me. That's the only way that I'm going to be able to really be able to do exams with this size of class. I've tried a few other things before. It's really hard to do exams through online systems. Unfortunately, due to the size of our class and the fact that we do have to social distance still, we are going to have to split our exams into 2 groups. One that will be on Tuesday and one that's going to be on Thursday of the weeks that I have in the syllabus schedule. I will make announcements about signing up for which group you're going to be in. So you will be able to pick up to whether or not you get there first. Obviously, I can't really do it any other way than that. But I will give you guys the option to sign up for which of the groups that you want to be in. The exams themselves will be normal paper exams. They'll be closed book. I'll allow you to have a scientific calculator. I don't allow graphing calculators or phones. I'll talk more about those when we get closer to the exams, and I'll be giving you announcements about the actual specific procedures, but just be aware of that. And then finally, we have office hours. So because we are online, office hours are a little bit more important than normal. I'm not going to be having that direct interaction with you guys through the videos. You're just sitting there listening to me right now. You're not giving me any feedback about what you want or what you are concerned about or what you might have questions about. So I will be having office hours. These will be on Tuesdays and Thursdays from 1 to 2 in the afternoon. These will be through Zoom, and you can get to them, get to the Zoom link through Blackboard. There's a link on the sidebar to join a Zoom meeting. If those times don't work for you, you can contact me and we can set up maybe another time. But I definitely encourage you to at least take advantage of these if you have any questions, or at the very least, you can also send me emails with your questions, and I'll be keeping up with those emails. I prefer that you use my email, my math email, which is my last name, Burkemper, at math.wichita.edu. Send emails there. I will get them, and I will respond to them as quickly as possible. I'm not going to guarantee that I'm going to be on at all times of the day, but I'll usually at least get to them in the morning or afternoon. evening I might be a little less attentive. But I will get to them when next time I see them. Okay, now that we've covered the course structure, let's actually get into some mathematics. What makes Calculus 3 distinct from Calculus 1 and Calculus 2? Well, it's mostly that we are going to try to extend a lot of what we did in those two courses to 3 dimensions. So we work in a 3-dimensional world, not just a 2-dimensional one, and so we want to be able to actually work with more general stuff. This does cause a few issues, such as making it a lot harder to graph stuff, but ultimately a lot of the computations that we're going to do is not going to be that more complicated than what we had to do in Calc 1. We're not going to have to necessarily to use all the complicated stuff from Calc 2. We will have to use some of the integration techniques, but I'll try to avoid any overly complicated integrals. They're technically still there, but we don't have to necessarily use all the more complicated stuff for our examples. And we're not going to be doing anything with series. Series are actually pretty useful if you continue on as differential equations, but they're not so important right now. Not that we can't use series in a 3-dimensional context, it's just nothing that we are going to be addressing in this course. I like to say that Calc 3 is actually easier than Calc 2 as long as you can visualize things in 3 dimensions pretty well. If that's an issue for you, you might have a little bit of difficulty here, but hopefully I can help you through that. In this first collection of videos, we're just going to be reviewing sections 12.1 to 12.4 because, like I said earlier, in Calc 2 at Wichita State, those are already covered. This is part of to lead into some of the physics-based classes. If you did not take Calculus 2 here and haven't seen this material before, make sure to ask me if you have any questions. At least read through the book. You get more detail there. I'm not going to cover every detail in these lectures, in these 2 videos, or more videos if I need to. But at the very least, I want you to actually read through it. Okay, so let's start off by discussing 3-dimensional space and graphing. When we graphed in 2 dimensions, we'd have our 2 axes. We'd have an x, that should have been a little bit more horizontal, but oh well. We have our x and y axes. And important things here is that these are at right angles to each other. Point has coordinates a, b, where a is how far we go along the x-axis. So this would be a, and b would be how far we go along the y-axis. In 3 dimensions, as you might expect from the fact that we call it 3 dimensions, we need 3 axes. Instead of x and y, we're going to end up with 3 axes. We kind of have to imagine these are in 3 dimensions. So imagine this one coming out of your screen. We're going to say that's x, y, and then we continue on with z. So we have points x, y, z, or let's just say a, b, c, where we have to imagine that, well, it might be a little easier to think that if we project it down here into the plane that's just spanned by x and y, we're getting a point AB, where the A and B are as we had it in our 2-dimensional system. But then, if we go over to the z-axis, that's our C. C is just telling us how far above or below the plane, the normal the normal 2D plane we are. So C is just an introduced height here. So you can think of the floor as being our XY plane, and you have your axes on there, but then your Z is telling you how far above or below the floor you are. Note that all 3 of these axes are going to be at right angles. They're all going to be perpendicular to each other. That's not possible to have three lines like that perpendicular to each other in 2D, but it definitely is in 3D. Each, and I talked about the XY plane a moment ago, so the XY plane, we can actually say this is the graph of the equation z equals 0. Essentially, here, every point in the XY plane is, say, AB0. The height over that is 0. But we can also talk about some other planes. We can talk about the XZ plane. This is, if you imagine just the x-axis and the z-axis, and just think about everything that's along this wall. Or in other words, you can say that's where y equals 0. Or you can talk about the YZ plane. That's so here now we're just using the y-axis and the z-axis and thinking about just everything along here and ignoring the x that's coming out of the screen. So there, x equals 0. So we've got all these various ways to actually break down our three-dimensional system. You can kind of think of these three planes as being, think about the corner of a room where you have the floor meeting two walls at right angles, and the two walls and the floor would be your XY, XZ, and YZ planes. That's an easy way to think about it. We are going to be a little bit picky about what order we put our X, Y, and Z on our axes. So with 2 dimensions, we almost always write it with the x-axis being horizontal and the y-axis being vertical. That's not technically important. Sometimes we do actually switch to x and y, though in a sense that's there's issues with doing that, but it comes down to the orientation. So what we want to have here is not necessarily exactly the way I have it drawn here, but we don't want to do something where we switch x and y, because that actually will change things. We want to talk about our orientation. And when it comes to certain operations that we're going to be doing later, orientation will actually be kind of important. We'll talk about that with the cross product specifically. But to make sure that we get the right orientation, we're going to use the right hand rule, where imagine using your right hand, you put your fingers along the x-axis, you curl your fingers in the direction of the y-axis, your thumb will always be pointed in the direction of the z-axis. So when I'm talking about the directions of these, I'm talking about the positive direction. So here, I put my arrow here on the x-axis. That's telling me that the x values are positive here, the y values are positive here, the z values are positive here. So my hand comes along, points along the x-axis, curls in the direction of the y-axis, and then my thumb is pointing in the direction of the z-axis. Might want to get used to that and see how exactly it works, because we are going to see the right hand rule again, and that's why I'm bringing it up right now. There's a reason why we're using that. Now, this is just kind of arbitrary. We at some point people decided to do it in this orientation. We could have chosen the other orientation and had a left-hand rule instead, but this is the orientation that we have that's been pretty well ingrained, and so this is one that everybody's going to be assuming that we're using. So it's just kind of the standard that we've settled upon. Of course, just like with 2 dimensions, we're not just going to be plotting points. Plotting points is just kind of boring. But we are going to be graphing equations. So just like we would have had something like y equals x squared, maybe here we're going to have something like z equals x squared minus y, something like that. The graph of such an equation is usually what we call a surface. There are some exceptions, but for the most part we will have just a surface. In order to be able to graph those, I suggest strongly that we use the program Geogebra. It's a very versatile program that handles graphing pretty easily. It you can use it to graph two-dimensional images, but especially with three-dimensional images, I don't really know of a better system. Um, you can get this on a computer. You can get this on a phone. There are apps that allow you to do that. Um, you have to you actually have to get different apps for two-dimensional and three-dimensional drawing, but it's all under GeoGebra. There's actually even just you can open up browsers. I don't know if the browser does 3 dimensions, but at least it does 2 dimensions. I I do suggest if you have a computer, uh, of course, just getting the GeoGebra program. So this is what GeoGebra looks like when you first start it up. You type in your equations here, so we could say y equals x squared down here. It'll give us our parabola. You can actually show or hide it if you want to. All the the graphs that you've done so far will be in this section over here. Now, of course, this is just showing 2 dimensions. That's what it does by default. Um, that's what the graphics view is. So if you want to look at 3 dimensions, you'd come up here to View and select 3D graphics, and they'll pop up with the 3D graphics over here. You can close the graphics if all you're looking for is the 3D stuff. You can rotate it around. It's pretty handy that way. And let's go ahead and maybe graph the equation that I said before. So z equals x squared minus y. And that shows us a surface here. So here, this up here allows you to either just drag stuff around like that, or you can go to rotate. Rotate's usually how you can get a better idea of what it looks like. And you can just look at what exactly this shape looks like. It's very, very handy. And it gives you a really easy way to get any idea of what that even means. And sometimes it'll actually change exactly what the format is over here. If you double click on that, it'll show you your original input. But it kind of will classify certain ones that it recognizes. But the point here is that this provides a very easy way of doing this. It's actually a lot easier than me having to draw these on a blackboard. That is one of the advantages of doing this in videos is I can show you on here really quickly and easily what a graph looks like, at least up to what GeoGebra is capable of doing. So we can look at some things. So something like z equals 3. So this is the set of all points that have a z coordinate of 3. And as you can kind of imagine, that's going to be a horizontal plane. Should mention here that if you don't like the color that it chooses for that, you can always set the color to be whatever you want it to be. So if I want that to be a lime green, I could make it be that. So if the color here that it automatically chooses is not good for you, you can always change that. And I guess speaking of which, they automatically put it in the XY plane. You can actually turn that off. I think it's this one, yeah. So if you don't want to see what that base plane is, you can turn that off and get it a little bit clearer. You can even turn off the axes if those aren't helpful. There's a lot of options here. Just kind of play around with it. I'm not going to go through everything GeoGebra is capable of. It actually is it has a wide variety of tools, so we definitely don't need all of them right here. You can also do something like y equals 5. So here, our y-axis is the green one. So here, everything that has a y coordinate of 5, and we get another plane. This time it's a vertical one, or a vertical one that's parallel to the x-axis, you could say. and Geogebra even recognizes those as being planes. We can have something that's a little bit more complicated. Let's type in our normal equation for the circle. X squared plus y squared equals 1, our unit circle. Of course, here, since we're working in 3 dimensions, we haven't said anything about the z-axis, and so it just assumes that we can let z be anything. That means we actually get a bunch of circles all stacked up on top of each other. So on the xy plane, this is just our circle. But then at, say, z equals 4, it's another circle. And so we get what we call a cylinder. Technically, this goes off infinitely in both directions, but that's what a cylinder is in a mathematical context. I can zoom in and see it a little bit bigger. I just use my mouse scroll wheel to do that. Um, if I zoom in a little bit more, I think I'm going to lose some of the axes. But it does zoom into where your cursor is, so it can take a little bit of finagling to get exactly the view that you want. So that's our cylinder, and it even recognizes a cylinder. We can do something like x squared plus y squared plus z squared equals 1. So instead of just having the x squared and y squared, now we can have a z squared in there. What does that look like? Let's get the cylinder out of there so it's a little easier to see. And that's one situation where you definitely might want to change colors when it just automatically chooses the same color. If I go into properties and change the cylinder to be, say, an orange, now it got a little bit darker when I clicked off of it. When I have it selected, it's different. Oh, there we go. Yeah. No, when I have it selected, it's darker. When I don't have it selected, it's lighter. But if I want to make sure that I can see one or the other and not have them interfere with each other, I can change the color to do that. But here, x squared plus y squared equals plus z squared equals 1, that gives me a sphere. Specifically, a sphere of radius 1. So here, let's... Come on, there we go. I want to move the z up a little bit so I don't cut off the bottom of the sphere. So I have my unit sphere, you could say. Or let's try something that's a little less standard. Maybe something like z equals cosine of x times y. And I think just a second. Okay, so it can be a little bit touchy when it comes to doing some of these 3D graphs. Apparently, if I write z equals cosine of x times y, it tries to make that into a curve. It works a little bit better if you leave out the z equals part. Here, it will actually realize that it is going to be a surface. So, what did it do there? There. So here is the graph of that surface. It writes it as a function of two variables. We'll be talking about how we deal with those in an upcoming chapter. Don't worry about that for now. Just we're using a of x and y as our z in this case. But it is a graph of a surface. It's kind of a complicated surface because of the cosine. So the cosine is giving you a periodic nature as you go along the x-axis. But along the y-axis, it just kind of works as just a number times y. And so you just kind of get some funky looking graph like this. And we'll actually be able to work with such a thing coming up later. We'll be able to find out things about the slope in a sense, though that we'll have to actually specify what that means in this context, and all that kind of stuff. Obviously, this is a little bit more complicated than what we will normally work with. It's just kind of a weird thing to see. Now, Geogebra will not be able to handle everything. If I typed in something like x squared plus 4y plus z cubed equals 2, it's not going to have any idea what to do with that. It gave us an undefined. It has no idea what I mean by that. And normally what you need to do is solve for z. So if I were to solve that for z, I'd have something like, so I go ahead and move everything except for the z to the other side. I'll get 2 minus x squared minus 4y. But then I also have to take the cube root, which I'll just do as a 1/3 power. It knows what that means. And why'd that give it to me as, oh. Alright, I put the z equals again. It doesn't like that. Here we go. So if I set z equals the cube root of a cube root of 2 minus x squared minus 4y, it knows exactly what to do with that. You get a kind of interesting looking surface here. But normally you either want to have it as, put your formula as z equals something in terms of x and y, or have some standard form. So like our sphere worked when we had x squared plus y squared plus z squared equals 1. That works because it recognizes that particular formula. But it doesn't recognize everything, and so we have to be a little bit more careful than that. If we do have a very complicated surface, sometimes what we can do with that is work with parametric equations. So you might remember parametric equations when it came to 2 variables. In 3 dimensions, we can work with those as well. Well, we will not be talking about those for quite a while. So normally what we'll do is set z equals something to work with it unless it's a standard form. We'll talk about some more specific surfaces in sections 12.5 and 12.6, which will be their own videos. But at the very least, we have our sphere. This sphere is an easy enough surface, and we'll talk about that right now. So you probably recall the Pythagorean theorem. This is primarily a two-dimensional formula that allows us to actually find distances in 2 dimensions. So in 2 dimensions, we have our distance formula, where if we have one point x1, y1, another point x2, y2, and we want to know how far apart these 2 points actually are, the distance is the square root, just because in the Pythagorean theorem we have distance squared equals something, and we have the difference in our x values, and I guess we'll put the x2 first. Difference in our x values plus the difference squared plus the difference between our y values squared, and that gives us the distance between those 2 points. Well, it turns out the Pythagorean theorem can be generalized to 3 dimensions. Think about a box. And I'm not drawing that very well, but oh well. Those should actually be a little more parallel. Whatever. So we have a box here, up to the limits of my drawing skill. And we want to talk about what is the distance between 2 opposite corners of the box. We can imagine a diagonal across the box. If the box has sides of A, B, and C, it turns out the length of the diagonal, which let's call that D, the diagonal squared is equal to the A squared plus B squared plus C squared. In fact, we can use the normal Pythagorean theorem to prove this. I'll let you try that out for yourself. It's actually not as difficult as you might think it is. You just might have to draw some diagonals on the faces. So instead of just looking at the ones that we have here, you might have to add in a few other lines into this diagram. But it's actually not that hard to do. Well, what that means is that we have a distance formula in 3 dimensions as well. And it's not too dissimilar to what we had before. So we have our 3-dimensional system. Remember, X is the one that comes out of the board. All right, so say board, but out of the screen in this case. We have 2 points. We'll say this is x1, y1, z1, and x2, y2, z2. And we want to know how far apart these are. Now, you can imagine these being very different. You can imagine very differently exactly where these points are situated in three-dimensional space. You can imagine maybe one of these points being a lot further into the screen than it looks. That's up to your imagination. Let's assume that we have actual numbers applied here. But the point is, once we have the coordinates of these 2 points, we can actually find our distance relatively easily. Here's the distance formula as it is in the book. So here, I guess I should probably label these as point 1 and point 2. The distance between those 2 points is equal to the square root of the difference between our x's squared plus the difference between our y squared plus the distance between our z's squared. So really the only change here from what we had in 2 dimensions is the extra term of z's. But it's basically the same formula, just a little bit longer, which is pretty handy. You just remember the regular Pythagorean theorem, and it leads very quickly and easily to this new formula for distances. That also means that spheres are a lot easier to do. Remember, so a sphere is just like a circle. So with circles, we have a radius and a center. If we have a radius r and a center hk, and we want to figure out what that looks like. So let's say here's our center. Maybe I'll call that O. And then we have all the points. Actually, let's make this solid. All the points with the same distance r from that center. And because of our distance formula in 2 dimensions, that has a nice simple formula of x minus h squared plus y minus k squared is equal to r squared. So here we were talking about a point xy that's on the circle. So let's say we have a point xy here. Remember, O has the coordinates hk, and the distance we want to have is r. So we're just plugging those into our distance formula, and then putting the square on the r instead of putting a square root on this side over here. Well, spheres are exactly the same way. We still have a distance, what we call the radius. We'll still call it little r. We have a center. This time we need 3 coordinates, of course. I'll still call this O, but it's going to be h, k, and because the book uses it, we're going to use L for that 3rd coordinate. We're going to make a fancy little curved L just to make it a little bit more distinct from a 1, basically. We're working in 3 dimensions now, so we have 3 axes. We have some point here. This is our center O, and we're looking at our sphere as being all points that are at a distance of r from this O. So a point x, y, z has to have a distance from hkl of r. That results in this equation here, where just like we had x minus h squared and y minus k squared, we now have, in addition, a z minus l squared. And I guess they called their centers c instead of o. Oh well. But the point here is that our formulas that we get are very similar to what we had in 2 dimensions, just with extra terms, just because that we have to deal with the z part of it. So, I mean, that's really all there is to say about spheres for now. We'll be using spheres very often, just because, especially when we get into some of the integration stuff, because they're fairly easy to work with. There's actually a whole system of coordinates that we will be talking about called spherical coordinates. They'll be based off of this, but for the moment, this is all we're going to be doing. like I said, we'll talk about some other surfaces and even some generalizations of what the sphere is in 12, mostly 12.6, but a little bit in 12.5. So I'm going to go ahead and leave this video here. I know this has gone on a little bit long. There's a lot of stuff to cover, but we also need to get into vectors as well. So we'll be talking about that in the next video. If you have any questions about any of this stuff, let me know. I can talk about a little bit more in office hours, or even I can bring it up a little bit in the next video if you do have any very pressing needs, any pressing questions. But I need feedback. Is really what it boils down to. All right, so I will see you guys in the next video, and goodbye.